In this video, we are discussing about the introductory ideas that are provided by the classical mechanics, which includes the accuracy or the help that we get from the Newtonian mechanics. Now, we had discussed a few points related to the Newtonian mechanics and where it really does not help us, not precisely, not the point exactly where it does not help us, but we had discussed that yes, Newtonian mechanics has its limitations, which are again made easier to or approachable by the likes of the Lagrangian and the Hamiltonian dynamics. Now, to begin with, we can discuss about the Newton's laws of motion. Now, the Newton's laws of motion, as we know it right from our school days, so we'll be discussing them in very short bits. That is, the first law, it simply tells us that until and unless an unbalanced external force, unbalanced external, and also the case being sufficient, if that kind of a force, when applied on a body, causes it to move, the body won't move or won't accelerate or won't change. There will be no change in its state of rest or motion. So this is the case with the first law, that an unbalanced external and sufficient force is required to move a body from or to change its state from rest or uniform motion. The second law tells us that if we are applying this force, then for the given mass there will be a change in its momentum with respect to time, and that force is equal to the rate of change of the momentum in the direction of force, and that eventually leads to mass times of the acceleration along the direction of the force. And finally, we have the third law, which tells us that for every force acted upon from body 1 over to the second body will also provide a reaction force which is exactly the same in magnitude but opposite in direction. That goes to tell that F is equal to F primed mod, but if you take it vectorially, then F is equal to simply minus F primed, or conversely we can say F primed is equal to the negative of F. So this is the action and reaction force which we have to be equal and opposite, but acting on two different bodies. As you can see, the object 1 applies a force on the object 2, the object 2 applies the other force, that is the reaction force, on object 1. Both the forces are not acting on the same body. So this constitutes the action and reaction case. Now then we move over to the case of inertial frames. And by the way, if you wish to know which law is important, well, the second law is exactly the real law which can explain both the other laws that we just have studied. Like for in case of this first law, the change in motion or the change in state of rest or motion causes what we know as acceleration, and the force that produces acceleration, that is described by the second law. And as for the case of the action and reaction cases, both acting on different bodies, well, their equilibrium is shifted if the forces are unequal, and with the shift in the equilibrium, or probably we can say that there will be a shift in the center of mass of the system of two particles, and if there is a shift in the center of mass, obviously the forces need not be equal. So in order that there is no shift in the center of mass, the forces must be equal in the absence of the external force. Now, considering the case of inertial frames, what we get to know is that if we let us consider two frames, the frames that we speak of are simply the coordinate systems that we can consider right now. So we have one coordinate system and another over here, and we name them. Suppose this is the S and this is the S primed frame, and it has a position vector supposedly from the first frame over here to the second frame over there. The origins are O prime in the second frame and O in the first frame, not O prime there. That's O. So O and O prime for the S and S primed frame. And we have the position vector of a particle in the second frame. For the second frame, it will be having a position vector, say R primed. And as for the case from the first frame, the position vector will be something different. We'll see about it, what it is exactly. Well, for as of now, we are naming it as R. Now, this second frame, S primed frame, supposedly it is moving with a constant velocity v. V here is constant. So it is moving with a constant velocity with respect to the S frame which is at rest. Now, initially at time t is equal to 0, the origins, they coincided. They were at the same point. Gradually, as time progressed, let us say after some time t, the second coordinate has moved to some extent. So the velocity that we are talking of, let us say it is going in this direction. So this line that we have over here will be having vt as its as the position vector in time t, because the speed is constant, so there's no acceleration involved. So the distance moved, or the displacement in this case, is simply velocity multiplied with the time. So from this, what we have is that this r that you can see in that triangle, that small triangle, very thin triangle, that is O primed, and let me name this point as P. So in that triangle O primed and P, what we get is that from the triangle law of vector addition, we get Vt plus r primed is equal to r, or r is equal to Vt plus r primed. That's from the triangle law. Further, we can take it as r primed is equal to r minus of Vt, vectorially of course. And what if we, now in Newtonian mechanics it is assumed that the time is universal. So this implies that the time of an event is the same relative to various observers in different states of motion. And what we get is, if we do the derivative over here, we are getting this as dr primed over dt, and then we are having dr over dt minus v dt over dt is 1. So this eventually leads to, well, if we take this as u primed and we take this one as u, so this is u minus v is equal to u primed, where u prime is the velocity in the s primed frame and velocity of the particle, because we are considering the change in position of the particle, and u is the velocity of the particle with respect to the s frame. If we do a second order differentiation, that is, we take the derivative once more, so what we get is du primed over dt is equal to du over dt minus, well, the velocity is constant, it does not change over time, so that goes to 0. Now du primed over dt will give us the acceleration a primed, and du over dt will give us the acceleration the s frame, which is a. So as you can see, we have the accelerations to be the same for the particle in both the frames, irrespective of the second frame going with a certain velocity. Now, the case of inertial frame is that when a frame is said to be inertial, that simply means that it follows the law of inertia, or Newton's laws. It obeys the Newton's laws, where the law of inertia obviously holds good. That means in the absence of external force, there will be no acceleration. So, a body moving with a constant velocity, now a frame in this case, moving with a constant velocity, right, that will experience, even if it was moving with a certain velocity, but the velocity was constant, so there was no acceleration involved. So with no acceleration involved, it won't really have or experience a different acceleration for this particle with respect to the first frame. The first frame's acceleration of the particle, of the given particle, and the acceleration of the particle for the second frame, as you can see, are the same, which means that if there is no acceleration for the second frame, it is also an inertial frame, which means that there is no external force acting on it such that it will accelerate and it will experience something different. So this result is a proof that whenever we are involving no acceleration, the frame is acting as inertial irrespective of any other reference frame that is taken with respect to. So any reference frame which is inertial, of course. Since S frame was inertial, S primed frame has to be inertial, moving with a constant velocity. Now, S, as we said, is an inertial frame. Now this transformation equation that we just did over here, these two, that is what we call as the Galilean transformation. We will learn about it in details when we study the relativity, the case of relativity. Now, what we are going to discuss is that in an inertial frame, we always experience the case of zero acceleration. It is unaccelerated. An observer every time in inertial frame won't see any acceleration in any kind of free particle which is devoid of an external force. Now, how actually are we going to observe such an unaccelerated reference system? Well, for a moment, we can think of the stars which are lying at a very large distance. They can be thought to be free from any interaction with the other bodies. And those fixed stars can be considered as a standard unaccelerated reference frame or the inertial frame. The sun, with respect to these fixed stars, moves with a uniform velocity, and hence a frame fixed on the sun is also inertial. A frame fixed on Earth is not inertial because the Earth is rotating about its axis and simultaneously it is moving in its orbit around the sun. The centripetal accelerations due to the spin and the orbital motion of the Earth are of the order of supposedly, let us say, 3.4 centimeter per second square at the equator, and likewise. So if a frame fixed on Earth and accounted for these accelerations will work well as an inertial frame, well, that is the case when the motions are negligibly small compared to the Earth's motion. A frame thus fixed on Earth can be approximated as an inertial frame. But that's a special case, of course. Now we come to the validity of the Newton's laws. Now the Newton's laws, the first and second law, do not hold good in accelerated or rotating frames. So there comes the case of non-inertial frames. Now the non-inertial frames are the ones which do not obey the Newton's law. That means you would probably obtain a case where there is acceleration in the absence of a force. When does that happen? Let's picturize something interesting that can give you what we are speaking, detail about what we are trying to get. Suppose this is a vehicle on a curved road. You and your friend are happily traveling in a vehicle. And that vehicle, what happens is that the doors, it's more or less like a Jeep, like the old days where it does not have really any doors. Now you are on the driver's seat, your friend is giving you company over here, and you're moving with at a good pace. So what happens is that there's this sharp turn that comes over here. Now you steer your wheel and you move in this direction, and your vehicle also takes that path, but unfortunately you, having put on your seat belts, your friend has forgotten to do so. So what happens is that there's a door which was over here, now has probably come over here, and as you move in this direction the door is probably here, and the friend is a free body. It's free because it's not connected to the seat, having not put on the seat belt, which is important. And what happens is that your friend continues to remain in a state of motion in that direction and flies off. And you tend to move along with the vehicle. Now, what happens to the observer who observes it from this place? Well, the observer simply sees that something got ejected out. Well, that something is your friend actually. So he is well aware of the Newton's laws. He is quite well aware of the Newton's laws. And he knows that there has to be a force which is causing this object to fly off with a certain acceleration, because in the absence of force, Newton's first law states that in the absence of force there cannot be any kind of change in the state of rest. Well, he was observing that the person, your friend, was seated next to you over here, and then all of a sudden he flew off in that direction. So he says that some force might have been applied. Maybe you have pushed him. He accuses you of pushing your friend out of the door, but you say that, hey, listen, this does not really happen. He was not putting the seat belt on, and I just turned in the track and my friend flew off. So both are correct in their way. But what happens to the case of the acceleration and the force? Well, this force that we are talking about is the false or the fictitious force which appears to be there considering the first law, but is actually non-existent. Your friend just held the direction of motion, and it continued to remain in its state of motion while you change the direction. So what happens in rotating frames is that in rotating frames, when you observe them, when an outside observes the rotating frame, he observes a certain force that is involved which actually does not exist. So that is the fictitious force. And that is exactly the case about non-inertial frame, even if they are just following their track, but the force or the acceleration still exists due to the presence of that fictitious force, and that fictitious force in this case is the centrifugal force that we are talking about. We'll discuss in detail about the case of non-inertial frames in the later topics that we'll come up with. As of now, I just gave you a brief idea about what we will be discussing then. Now we move over to the discussion about the gravitational and the inertial mass. The inertial mass, as you might have thought, if the inertial frame is where the law of inertia is uh, well kept, or holds good, then inertial mass may be something like that, where the law of inertia for the given mass is going to hold good. And as for the case of gravitational mass, we have the case of gravity involved in it. Now, gravity, as you know, is that force which causes attraction between two masses. So let's consider the mass of the earth and the mass of an object, mg, where mg is the gravitational mass that we are talking about. And here r is simply the radius of the earth. So the earth attracts with a gravitational force. This has been written in case of magnitude. In case of vector consideration, the force would have been a negative one in this case because it's attractive in nature. So what we get from this is that we get the gravitational mass of the object to be equal to all these mostly constant terms, F being the force due to the gravitational attraction, r being the radius of the earth, g gravitational constant, me mass of the earth. Now, inertial mass, let us suppose we have an object which has an inertial mass m1. Now, inertial mass is something where the law of inertia holds good. That means it is acted upon by a force, then only it tends to accelerate, and if it is at rest, well, it continues to stay at rest unless acted upon by an external, unbalanced and sufficient force. Now, two things that I would like to give you an example about why this is inertial. Well, inertia, as you know, when we are considering the case of inertial masses, the Newton's law come into account, and what does it say? Well, in the first case, the law of inertia states that a body continues to stay in its state of rest. So if this mass was at rest, supposedly, there would be some gravitational force acting on it. This is the force due to gravity, the very force that we are talking about over here. And what happens is that you provide it with a force which is not sufficient enough, so it does not move. Then you go on increasing the force, and then it thinks about moving, and if it is sufficient enough, then it goes on to move. So here the external force that was applied was sufficient enough to negate this attractive force by the gravity on the other side. So this mass m1 that was obviously attracted by the gravitational pull, that is the same which is following the Newton's law. So this gravitational mass is also being treated as the inertial mass. Let me give you one more example. You have two bodies, supposedly m1 over here and a much more massive m2 over here, and both are set into motion with a velocity equal in each case, that is v, and then they are to be stopped over here at this very point. Now in order to stop this, the change in momentum that will come is m1 times of v minus 0, because the final momentum will be 0. We'll take it the other way around. Usually it's the final minus the initial, but as a magnitude we are considering the change in momentum. So the change in momentum is m1v minus 0, or 0 minus m1v, so I have taken the modulus, and the time that is taken is supposedly del t. Now m2 is much greater than m1, and in order to stop this over here, it will be moving at this point. Just before stopping, it will be moving with a velocity m2v, which is much greater than, because v being the same in both the cases, m2v will be greater than m1v, and the final velocity will obviously be 0, but the time taken in each case is also maintained at del t, which is the same. Now which of these factors will be greater? Obviously m2v minus 0 is much greater than m1v minus 0. That means you will require a greater force. What is the change in momentum over time? Well, that is simply force, the second law. So you will require a greater force in case of this, rather than in case of the first object, that is m1. So the momentum, that's because the momentum contained in the second object is much more when compared to the momentum of the, or the change in momentum in this case is much more for the second body as compared to that of the first body. And that change in momentum is occurring for the masses that have been considered, which again gets us back to the inertia, law of inertia, that the force required to bring about a change in the state of rest or uniform motion, in this case it is uniform motion, in the previous case it was case of rest. So the force that is required to bring about a change in the state of rest or uniform motion is equal to mass times the acceleration, because the change in velocity is obviously leading us to acceleration, and it is greater for a greater change in momentum, it is less for a less change in momentum. So all of these cases, that leads us to, now imagine if they were, if they were in space also, the same condition applies where there is microgravity. Now, so what we get to know from these two analysis is that this, if we take the ratio of the first, of the inertial mass of one of the objects, and then over the gravitational mass, and for any second mass that we consider over the gravitational mass, what it has been observed is that this comes out to be a constant, and this constant, by suitable choice of units, is obtained to be 1. So the inertial and the gravitational mass are not distinguishable, they are one and the same, and that is known as the principle of equivalence. That is known as the principle of equivalence. Now we are quite familiar about the conservation laws, and so let's discuss a bit about these conservations. So first up, we have the force to be equal to the rate of change of momentum. Now if the external force is 0, then obviously we have the change in momentum to be 0, and so that gives us the conservation of linear momentum, that is m times of v, that we used in the previous examples. And then secondly, we can consider the case of angular momentum. So the angular momentum is usually denoted as J or sometimes as L, and it is R cross product with the linear momentum. Now the torque is the angular force that we speak of. So the torque is equal to R cross F. And when we take the derivative of the torque taken leads us to, not the derivative of torque, well, the derivative of angular momentum with respect to time, that leads us to torque, because angular force is equal to angular rate of change of momentum, or the rate of change of angular momentum. So in this case, if the external torque that has been applied on an object, that is zero, then we have the case of the conservation of the angular momentum. So this is a constant. Oh, I beg your pardon, I haven't written a constant over here, I've set it to zero. So this remains constant, or this is conserved. So silly mistake from my side on this case. So this is P is constant, that is the linear momentum, and we have J as the constant, that is the case of angular momentum. Now if we are considering the case of work that is done, now we know that the work done is equal to the force times of the displacement, and in case we are considering kind of displacement from one place to another, that is from 1 to the point 2 in a certain path, well, in this case the force is taken as the dot product of the displacement at each point, and we integrate it over that entire path. And as far as the case of kinetic energy is concerned, the kinetic energy is equal to simply half mv squared, right? So let me use the space available over here to complete this discussion. Now if we are considering the force times of displacement in that very figure that I have shown you over here, so what we get is F dot dr is equal to m times of dv over dt times of dr. We can say that, because force is mass times of acceleration. Acceleration is dv over dt, that is the derivative of velocity with respect to time. And if we take this one dr, that is simply equal to v dt. So m dv over dt times of, or dot product with, v dt. And if we take it as one term, that is m d over dt of half of v dot v, because that's going to be v square, and the derivative of it is going to give us a 2, which will cancel out the half, so we can include a half over there. Now this is equal to, well, now we can take the m inside and we cancel out the dt, so this is giving us d of half mv squared, which is the kinetic energy term. So F dot dr is the derivative or the differential of the kinetic energy, and when we are integrating it from the first point 1 to the next point 2 to obtain the complete work, which was the case with F dot dr taken from 1 to 2, well, in that case we are ending with the kinetic energy at the final point, that is at 2, minus the kinetic energy at the first point. So this is going to give us a change in kinetic energy. So the change in kinetic energy is equal to the work that was done. Conversely, the work done is equal to the change in kinetic energy. So this is what we call as the work energy theorem, important in terms of what we are moving towards in this in our topic of discussion, in the especially in the preliminary case of the Lagrangian dynamics, and many more things to come. Now next we can consider a case where we are considering the same figure that we had come up with in the first case. So there was a force acting and a particle. It was supposedly moving from the point 1 to the point 2, and some work was done. Force was the dot product of force with the distance with the displacement gave the work that was done. Now the force will be said to be a conservative one if it is not dependent on any path that is taken in order to move the object from the first or the initial to the final point, be it the solid line or the dashed path. It does not matter in which direction was the force applied, the result would be the same. So the work in the path, let's say this is the path A and this is the path B, so the work done for the path A will be the same as work done for the path B, and that will give us a conservative force, or force which is conservative. Now thus, for a conservative force, what we can see is that we have 1 to 2 in the path A to be similar to that in the path B. That means what we can say is we can keep that A from 1 to 2, and we bring the B to the other side. And if we are bringing it over to the other side, it's going to be minus, but I'll keep it as plus, and I'll just change the limits that we can do, that is from point 2 to the point 1, f dot dr. What that gives us is that 1 to 2 and then 2 to 1 is simply a cyclic path, and that is equal to f dot dr, and that is the integration over f dot dr, and that is finally giving us 0, because these two were equal in magnitude. When this thing came back to the other side, obviously it will be minus the same thing, and that will lead us to 0. And one way of interpreting it over that closed path 1 to 2, 2 to 1 will be that integral with the circle. So that is the case of conservative force. And if the force is conservative, then the work done on the particle around a closed path in the force field is going to be 0. Now in case of a non-conservative force like the friction, supposedly, the amount of work done around that different closed paths, that will be different. That won't be resulting in a 0, because some of the energy will be getting invested for sure. So in that case, that will be non-conservative force, because what you are going to see over here is that from vector analysis we can also say that f dot dr over that closed path is equal to the curl of f dot ds, and that is going to be 0 for conservative force. ds cannot be 0 for sure, so what we get from this is that curl of f is equal to 0. Therefore the force can be expressed. Now this is possible when this second thing of which we are getting the curl of, when that is equal to 0, that means the curl of that thing being 0, that thing must be gradient of something. So the force here is a gradient of what we call as the potential energy term. So the force is the negative gradient in this case of the potential energy. The minus sign has appeared, you might think out of nowhere, but that's from the calculation point of view. So this minus sign along with this gradient will give us I hat del u over del x, just the case of that gradient operator being written explicitly as I am doing it right now. That is the partial derivative with respect to each of those coordinates, that is x, y and z. And with this Curl of this will lead to 0 only when we have this case. So this is the scalar function and it is known as the potential energy term. And it depends only on position, not the path taken. And since we are bringing it back to the same point, that is why the potential energy remains the same and there is no change in potential energy, and as a result of that we are not getting any kind of work over that closed cycle. So considering only the first case, that is from the point 1 to the point 2 over that path A, so we have f dot dr to be equal to the negative of the integration from 1 to 2 del u of not del u, it's gradient of u dot with dr, and that's going to give us a du integrated from integrated from 1 to 2 over that negative path or that negative integration, and that will give us u1 minus u2. I'm keeping it as u. In many books you will find it as v, but I'm keeping it as u for now. If we are considering this first place as infinity, then we obtain the potential energy will be 0 in that case, and for the point 2 that we are considering, the potential energy will be like this, that is u of r at the position r, which is at the point 2. So point 2 is having a position r, suppose. So this is going to be f dot dr taken from infinity to r in negative, and that's going to give us the potential at the point r, or at the position r, from a reference point. From that reference point we had the other point, that is the initial point, to be at infinity, that is at a very far distance. Infinity here simply means a very far distance as compared to the position vector r in this case. Now since this was giving me the work done, so what we get from this is that, well, it has come to the same place, so the position being the same, there's no change in potential energy there, so the potential energy change is 0. But for a finite work to be done, for finite work, we move from the point 1 to the point 2, then we get the change in potential energy as simply del u. So this is also the case of work energy theorem, where the potential energy is changing, and the change in potential energy, since it is taken in the negative form, so we'll have u1 minus u2. In completeness, what we learned is that work done from 1 to 2 in the first case with the kinetic energy term was the final kinetic energy minus the initial kinetic energy. As I was indicating, we can write it as T2 minus T1, T2 being the final and T1 being the initial. Also the case with the potential energy, what we obtained is that is simply U1 minus U2. So what we get from this is T2 minus T1 is going to be equal to U1 minus U2, or we can take them to, we can change sides, and what we find is T1 plus U1 is equal to T2 plus U2, which means the total mechanical energy, which is the sum of the kinetic energy with the potential energy, that is always going to be a constant. So that's the conservation of energy that we have just studied. Another conservation law. So this is more or less the case of one particle system that we studied in this video. In the next video in the series, we'll be continuing with the introductory idea. That will be the last part of it, and there we'll be discussing all of these conservation laws for the many particle system. Till then, thank you for watching.